Next, we are going to introduce a very important and usually is much more important than linear amplification using operational amplifier. It's called filtering. Okay, what is filtering? Let's see what it writes in the slide. A filter is to eliminate. A filter is to eliminate the signal within the undesired frequency band. But the more general use of the filter is to alter the signal within certain frequency band. As you can see, it's altered. It's altered, not necessarily eliminated. Traditionally, it's eliminated, but in the general use, it's altered. You can make it bigger, make it smaller, either way. And in the right-hand side, there are some very typical filter. Okay, the first one is called the low frequency. And what is a frequency band? Okay, we have frequency band. This is the name, the frequency band. And in general, this is a low pass filter. And usually we draw a line here. We call this one is the cutoff frequency. Meaning that this is the kind of boundary that lower than this boundary, we have the one kind of processing, and higher than this boundary, we have the other kind of processing. So it's cutoff frequency means it is the frequency that divides two parts. So in the x-axis, this is frequency. Usually in hertz, which is over 1 over seconds, or radian per second. Okay, this is radian per second here, or this one is hertz, one is radian per second. And when we call this as low pass filter, means that in this frequency band, what is the frequency band? The frequency band higher than the cutoff frequency. We want to eliminate the signal. And we call it low pass because we don't change the content of the signal if it's lower than the cutoff frequency. Okay, so we call it a low pass filter. Of course, you can say it's a high rejected filter, or you can say high reject filter. It's also okay, but usually we just call it low pass. And this one, reversely, this one is the high pass filter. We have the FC over here. We try to cut frequency from this part, and we try to preserve the signal on the right hand side of the cutoff frequency. And this one is called a band pass filter. The band pass filter has two cutoff frequency. We have cutoff frequency L and then cutoff frequency R. And we try to eliminate the signal from both sides and preserve the signal in the middle part. Okay, so that's why we call it band pass. So in this band, we let the signal pass. But out of this band, we don't want the signal, so we eliminate it. So this is the band pass filter. And the other one, okay, called the band stop filter, we also have the FCL, we have FCR, but we try to preserve these two parts and try to eliminate this part. So this is the band stop filter. Okay. So the other one is very similar to the band stop filter. It's called a notch filter. Since I write here, it's a notch filter. Notch filter has this kind of characteristics. It's kind of it has a filter, something like this. The purpose of notch filter is just take off the content of the signal at a specific frequency, for example, 60 hertz. And because 60 hertz usually the noise come from our power line, and usually it makes a lot of the trouble when we analyze signal, so we want to take it off. So this one is not filter. It just try to eliminate a specific frequency signals. So this is the we call it notch filter. Okay. So in this semester, we just teach you about all the how to use the operation amplifier to implement this kind of very simple filter, especially low pass filter and high pass filter. Okay. Then what does the frequency response mean? Okay, we have the name called the frequency response. Frequency response. The frequency response means that if we have something like a filter, okay, and we have signal goes in, we have Vs of t, and we have Vs out of t, V out of t, and we want to know the characteristic of this filter, and the characteristic of this filter usually has been stated here. Is a low pass filter, high pass filter, band pass filter, band stop filter, or even notch filter. But there gotta be some spec to describe the filter. And one of the way to describe the spec of the filter is that we use the magnetic response and the phase response. And sometimes we call, because it is measured in frequency domain, meaning that x-axis are frequency, so we call it frequency response. So as you can see, this is the one. And usually we will not use linear scale in the graph. So here, this is log scale, and the dB is also log scale, which will be explained later. Okay, so we have the cutoff frequency, which is called FC, cutoff frequency here, and we have cutoff frequency here, and we have a pass band. We have the pass band here, and we have the stop band here. Okay. And this one is the phase. This is the degree, the phase response. For example, this one is minus pi over 2, for example. Okay. And there are some couple of terms that need to be explained. Let's go back. Let's leave the first order and second order later. Okay, let's first talk about the octave and the octave and decades first. Let me erase this. Okay, so if we have a frequency f1, if we have frequency f1 and f2, if f2 is 2 times of f1, then we call f2 is an octave higher than f1. Okay, but if f3 is 10 times of f1, then we call f3 is an decade higher than f1. And by showing in this graph, if this one is 10 hertz, then because we take log 10, so here will be 100 hertz. And here will be 1000 hertz. And of course, 100 hertz is a decade higher than 10 hertz. And 1000 hertz is a decade higher than 100 hertz, and also 2 decades higher than 10 hertz. And because we take a log, a base 10 log, so here will be 20 hertz. Okay, so we know that this is an octave, but this will be a decade. Okay, that's the first term we want to explain. Okay. Then next go to the explanation of the dB. For example, let's introduce OSDP. So for example, V2 is equal to 2 times of V1. And how to calculate dB? dB is something like you have to do it in comparison. Means that also in comparison with the V1 compared to V2. So the dB when is written as 20 multiplied by log 10 and V2 over V1. No. I will make it this one 0.5. And this one become 20 log 10 0.5. As you can see, this one is minus 6.02 dB. Here, we call it dB here by this formula. So as you can see, there are some figure. So if V2, so if V2 is 1 over square root of 2 of V1, and that would be minus 3.01 dB. And usually we'll discard the 0.01, the 0.02 here. Okay, doesn't hurt. Okay, as I say, the electronic circuit is something like approximation. After approximation, there's approximation, and 0.01 is only a small fraction, so it doesn't hurt. Okay, but if V2 is 10 times, it's 0.1 multiplied by the V1, then will be minus 20 dB. Because we use, if you remember, we use base 10 log here. By showing it here, we'll see that the cutoff frequency FC is always located at the minus 3 dB place. And this one will be minus 6 dB, and this one is minus 20. So this 1/2, this 1/10. And from this part, from the cutoff frequency, this part, and if we have a decay of frequency difference, and this signal is attenuated by 10 times, means the magnitude now becomes 0.1 multiplied by the original signal, and this is 20 dB per decade. This is how we call minus 20 dB per decade. And if the filter is minus 20 dB per decade, we call it is first order. And what about the second order? Second order is minus 40 dB per decade. And of course, we can know that what about the third order? Will be minus 6 dB per decade. Okay. So these are basically the frequency response, but especially in magnetic response. But what about the phase response? Okay, let me explain what is phase response. for the phase response, okay, we have to say that is referred to the sine omega t. So the phase is especially referred to the omega here. So omega is equal to 2 pi f. F is the frequency. Meaning that at specific frequency, how much is the phase altered? For example, if I use this one, for example, at 10 hertz, I believe it's 10 hertz here, 10 hertz here. Okay, then at 10 hertz, okay, omega will be equal to 22 pi multiplied by the 10, which is only 20 pi. But this filter makes some change to the original signal, and the phase become minus 90 degree. And minus 20 degree is minus pi over 2, right? So if I have a signal sine omega t, but now because omega is 20 pi, will be 20 pi t minus 1 over 2, pi over 2. But let's take out the 20 pi of the t. I have pi over 2, 20 pi here. Okay, let me go further. I have a 20 pi t minus 1 over 40. What does this mean? This means that the signal of 10 hertz is delayed by 0.025 seconds. Let me draw it. So if I have a sinusoid here, if this is my input here, then the signal will be delayed by 0.025 seconds. 0.025 seconds here. This is 0.025 seconds. So as you can see, that it's quite simple to imagine that, because 1 over pi over 2, okay, will be we know 2 pi means that we have the complete circle of the sinusoids, and 2 pi over 2 is 1/4 of a cycle, right? But a cycle, because 10 hertz, so a cycle means 0.01 seconds. So the delay will be 0.01 second divided by 4, which is 0.025 seconds. So these are the same. So this is the phase difference, meaning that a filter can also alter the signal in this way. It delay is a signal in a signal of 10 hertz by 0.025 seconds. Okay. This is the phase response. Okay, but in this method we will only talk about the magnetic response, but the phase response I just want to let you know.